Hey, this is Ari, and in today's lecture, we are going to be covering the data structure of skip lists. So we are going to cover the introduction and motivation of this data structure, the components and structure of it, its operations, how it works, then a little analysis on complexity, and then some pros and cons to finish it off. Okay, so what are skip lists? Basically, skip lists are a modified sorted linked list that have the base linked list and then uh, multiple express lanes that allow you to traverse and search the linked list a lot quicker. Um, they are an alternative for binary search trees, and the advantage that they provide is that they speed up the search process from a base linked list and provide a simpler way to do that than using a BST. They're not necessarily needed anywhere, but sometimes they are optimal compared to linked lists or BSTs, and we'll get into that more on the complexity slide. They were invented in 1989 by William Pugh, and as far as real-world applications, they're used a lot in database indexing, such as in Redis or LevelDB. They can also be used to implement a priority queue, and obviously the simplest implementation is just a substitute for a BST wherever you might need a BST. As far as the structure and components go for skip lists, the base structure is a sorted linked list, which is often called level 0. It's at the very bottom on that diagram there. And above it are the express lanes, which are basically parallel linked lists that contain fewer elements each level you go up. And these are created on insertion. When a node is inserted, it randomly gets assigned the amount of levels it's going to be on um, via the promotion probability variable P, which is the threshold of that. So basically, a when it's inserted, a node is guaranteed to be on that level 0, that sorted linked list. And then let's say P is half, then it's basically like a flip of a coin. There's 50% chance that it will also be implemented on the next level, level 1. And then from that level 1, there's a 50% chance it's going to be implemented on level 2. And then 50% chance from there it's going to be implemented on level 3. And then say that p-value is like 1/4 instead of 1/2, then that's just like a 25% chance that it moves on to the next level. Um, as far as comparisons to other data structures, it is is similar to the linked list in that it includes a linked list within it as part of its structure. But purpose-wise, it's more similar to a BST in terms of complexity and the purpose. Okay, so as far as operations go, in the next few slides, we're going to walk through a basic case of search and then insert and then delete. As far as special or edge cases go, here are a few listed. For search and delete, if you're looking for a node that is not in the list, that's going to be an edge case. For all three operations, if you're looking for the smallest or largest value, that's going to be the one on either end. That's going to be an edge case. Then for search and insert, if you're trying to do that on an empty list, there's going to be an edge case. And then for search and insert, if you're looking for a duplicate, that's going to be a special case. So they're all pretty simple to think out, but just take note of those. Okay, so we're going to walk through an example case of the search operation. As you can see here, we have an example skip list, and we're going to be searching for the node 7. So for the search operation, you're always going to start on the first node of the highest level. As you can see, I have that circled here. That's that one node. And you're just going to continue moving along the nodes of that level for as long as the next node is less than your target. So as we can see here, our next node is that 5 on that level 1, and that is less than our target value of 7. So we're just going to move on to that 5, make that 5 our current node. So now that 5 is our current node, we're going to check its next node, which is 9, which is not less than the target value of 7. So we are going to go down a level. So as you can see by that circle, we've moved down to the 5 of the level 0 there. And now basically we're just treating it like a linked list that we're searching through. So we're just checking, is 5 the target? It's not, so we're going to move on. And 6 is still not the target, so we're moving on. And now we found the target at 7. Okay, so now we're going to run through an insertion operation. We have our sample skip list here, and we are going to try to insert 8. So the procedure for insert is we're going to find the predecessor to our node on each level. So we're going to start again on the first node of the highest level. We have that 1 circled here, and we're going to check if the next node is greater than the target node. If it is, then we know we found our predecessor. So in this case, our target node that we're inserting is 8, and 8 is less than our next node of 26. So we know our predecessor on this level 1 is going to be the current node 1. So we're then going to go down to the next level and find the predecessor on that level. As you can see, we've now moved to this 1 node on level 0. And we're just going to do that same search for the predecessor. So currently the next node is 3, which is less than our insert node of 8, so we're going to move on. So the current node is now 3, the next node is 7, which is still less than 8, so we're going to move on. And now that the current node is 7, the next node is 13, which is now greater than 8 that we're inserting. So we've found our predecessor on level 0, which is 7 in this case, the 7 node. So now that we've found all the predecessors on each of the levels, we are going to determine how many levels we want to insert 8 on. So in this example, we're going to be using a p-value of half. If you recall, that's the same as flipping a coin to decide if it's going to be or if it's going to move up a level or not. And I don't know if I mentioned this earlier, but skip lists often use a max level, which is basically just a hard cap on the height of the overall data structure. So for simplicity's sake, we're going to keep the max level of our example at 1. So if it moves up to level 1, we're just going to immediately stop it there. So imagine we have a random number generator that either generates a 0 or a 1. And if it generates a 0, then our node is just going to be inserted on level 0, and it's not going to move up any levels. That's it. Let's say in our case, it generates a 1, meaning it moves up to level 1. So it's going to be it's going to be inserted on level 0 and level 1. And in normal cases, we would generate another random number to see if it moved on to level 2. But since we have that max level cap at 1, it's just going to stop there, and we're going to insert it on that level 0 and level 1. So as you can see here, we inserted the node after the predecessors that we found earlier. On level 0, that's 7, so it goes 7 and then our node 8. On level 1, that predecessor was 1, so it goes 1 and then 8. And then we just fix all the connections for the lists. Okay, now for our last example operation, we're going to be showing the delete operation. We have our sample skip tree here, and we're going to be trying to delete 5. So for the delete operation, the procedure is just going to be just like the search operation was. We're going to search through it, and if necessary, we're going to record the predecessors like we did in insert, and then we're going to do the deletion. So like always, we're going to start at that first node of the highest level. We have it circled here, and we're going to check its next value, which is in this case our target of 5. Since we've found that our next is our target, we know that our current one is the predecessor for our deletion. So on level 1 here, we know our predecessor is 1, so we're going to move down level and continue this process for the next level. We've now moved down to level 0. You can see we are that circled node here. And we're going to check the next value. In this case, it is 2, which is less than our target of 5, so we're just going to move on. Now our next is 3, which is less. Now the next is 4, which is still less than our target. Now finally we have our next is 5, which is our target. So we know that our current node 4 is the predecessor for level 0. So now we found the predecessor for each level of our skip list. On level 1, that predecessor was that first 1. And on level 0, that predecessor was 4. So now we're just simply going to connect the predecessor, the next pointer of the predecessor, to the node after that target. And then we're just going to delete the target. Now on to complexity. So here we have a table for the time complexity and a table for the space complexity. As far as the time complexity goes, for the average case of a skip list for all 3 basic operations, search, insert, and delete, it's going to be O of log n. And then for the worst case, it's going to be O of n time. And as you can see, we have the time complexities for a normal sorted linked list here for comparison, and that's just always going to be O of n time. And then for space complexity, the skip list is going to have an average of O of n and a worst case of O of n log n. And then the sorted linked list for comparison, it's just going to have both average and worst as O of n. And I will explain some of the details on why these numbers make sense in the next slide. Okay, so here we're just going to dive into some of the details on why the time and space complexity of those skip list operations make sense. For the time complexity, skip list has O of log n average time complexity for all of those operations, because assuming the p-value is half, right, that's our coin flip, each level has about half the elements of the level below it, or in other words, when you're on that level, you're skipping about twice as many elements during an operation. So there are about log base 2 of n levels that you're going to visit, and on each of those levels, the amount of work you do is constant. So the total work is going to be that log base 2 of n times a constant time operation, which is a total of big O of log n. And then for the space complexity, we have that as n log n worst case, because we're assuming that most implementations have the height capped at log n. And in this case, if our height is log n and every node in the list is assigned to every level, right? This is our coin flip. It just happened to land on heads every time for every element. Then we're going to have n nodes at each level, and there are log n levels. So you just multiply those, and that's n log n nodes. Okay, so as far as the pros and cons go for a skip list, the biggest advantage you're getting is the time complexity, which we just discussed is on average log n, which is much faster than a normal sorted linked list, which is normally O of n time. And the disadvantage, that trade-off you're making for that time efficiency, is the amount of space it takes up. The skip lists are going to be bigger than, say, a sorted linked list because it has those extra levels that it has to maintain space for. So you should be using your skip list when space is not really an issue and you're really valuing your time efficiency. Apart from that, some things to consider about the implementation of skip lists is that it relies on a random number generation when deciding how many levels to insert a node into. So it's not going to be consistent, and we saw that with our complexity calculations where the average case was different than the worst case because of that. And some other things to consider is that the p-value and the max value are up to the programmer to decide, so implementations may vary on that. And here's a list of the sources I used. Feel free to look into that. Thank you.